On July 16, 1945, the first nuclear weapon was detonated on the plains of New Mexico. Not only did it mark a terrifying point in human history, it may also have heralded an extraordinary shift in our natural world, which none could have foreseen.
The bomb spike can be detected in layers of ice and snow on the polar ice caps. It fell over land, it fell into peat bogs, it fell into lakes. It is not the most important of the changes.
Around the same point in time began the Great Acceleration, a period of socio-economic growth so rapid and profound, it dramatically altered the way our planet functions.
Greenhouse gases are increasing at an enormous rate. Temperatures rising. Atmospheric circulation is changing. Nitrogen is accumulating on land and in water. Ocean is acidifying. Species are being lost. The entire fabric of the planet is being made over at a very rapid rate.
Our impact has been so extreme, many scientists claim we're now living in a new geological epoch. Because long after we're extinct, the scar of our existence will be visible in the sedimentary rocks that form the foundations of a new world.
As a geologist, I think it represents a very dramatic change in the nature of the materials deposited on the planet.
In the blink of a geological eye, have we entered the Anthropocene? Formally, we're still living in the Holocene, which, as geological epochs go, has been extraordinarily short-lived. It began around 12,000 years ago, and it's characterised by an extremely stable climate, ideal for us.
Well, this particular epoch in the history of the Earth is really a golden time. It is the Goldilocks time, in fact. It's not too hot and it's not too cold. It's just right for human civilization to expand. Unfortunately, of course, maybe we've expanded too much.
So basically all of our human civilization sprung up during this time.
Absolutely. So this has been the time for agriculture, pastoralism. People have done well on almost every continent except Antarctica. I think we don't know how lucky we are. It just could be so much worse.
To understand how profound it is to leave the Holocene, we're going on a journey back through time, through the stunning Flinders Ranges.
These ranges are about 500 to 800 million years old. This whole ocean basin was compressed, and these once horizontal layers of sand and mud and lime were buckled up into giant folds. And that's why today, as we drive through places like Bratchner and Bundaroo Gorge, we can see the whole succession, layer by layer, as we drive from one end to the other. We can go down through time.
So Anya, this is the place I really love to come. Have a look up there. That's nature laid bare.
Geological time units are marked by changes in the strata that occur globally. They represent distinct events in the Earth's history.
So the amazing thing about this area is that you can go up to a particular layer and you can examine it in detail, and then you can go to the next one, and that's actually a tick in the clock of geological time.
They're really beautifully distinct, these colours.
It's a change from shallower water to deeper water, from a time when there were no animals to a time where you get the first animals. And those changes are very important because we can then use this as a kind of a logbook in rock that you can compare with the geological record on another continent. That's what makes the Flinders Ranges very important.
This section of the logbook chronicles the Ediacaran period, which gave rise to the first multicellular life on Earth. exposed sections are like illustrated pages of time, with detailed depictions of individuals that lived 550 million years ago.
This thing called Dickinsonia costata is a mat-like animal. This was the anterior or front end, and this whole assemblage represents a sample of a seafloor community. This is quite a shallow marine environment.
What gave rise to this explosion of life? In a creek bed in Bratchina Gorge lies an important clue. If you weren't looking for it, you'd be forgiven for walking right past it. But this small brass disc draws geologists from all over the world. It's known as a golden spike.
There it is. This is the golden spike. Spike is in the rock. This is the disc with the crosshairs marking the level that is the global position for the base of the Ediacaran period and the end of the Cryogenian period. Probably the most massive series of ice ages that the Earth has ever experienced.
There was so much ice, the period was nicknamed Snowball Earth. Large dropstones set in the darker rock beneath me are evidence huge glaciers once moved across this region.
And what made it transition from Snowball Earth to the Ediacaran? What change happened to the Earth system?
The argument is that volcanoes continue to exhale carbon dioxide into the atmosphere. Once the ice had actually melted, the carbon dioxide continued to build up and warmed up the atmosphere again, and it became possible for the next stage in the history of life.
The golden spike here in the Flinders is the chosen place in the world to mark that transition in the rocks.
When you actually have changes in the geological record, often they're just local. But we can demonstrate that this is truly global. And it's that change that had to be marked somewhere on Earth, and this is the place.
The transition to a new geological time unit isn't always marked in rock. In fact, the golden spike for the start of our epoch, the Holocene, is in a freezer in Copenhagen. It's an ice core that records the abrupt and dramatic shift in climate that took us out of the Pleistocene.
It's incredible to think that the rate of rise of atmospheric CO2 is now around 100 times faster than the most rapid rate during the end of the last ice age.
But is that enough to declare a new geological epoch? Humans have always made an impact on their environment, like many other species. Think of locust swarms, mouse plagues, or even methane-emitting bacteria. What makes this period so different is our impact on the global environment has now become so large, we're changing the structure and function of the Earth system as a whole. And it's all happened remarkably fast.
So rapid and so big in magnitude that it looks like a meteorite strike, not like anything else that biology has done in the past.
It's fitting that I meet Professor Will Steffen in our nation's capital, Canberra, a city that didn't even exist before 1950. Even this lake is man-made.
There was virtually nothing here. There was old Parliament House, a few sheep paddocks, maybe one suburb, and that was it.
Will is a world leader in Earth system science, a community from which the term Anthropocene, meaning the new age of humans, first sprung.
So all this is been created during the Anthropocene.
Canberra's population, suburbs, services and infrastructure have expanded dramatically in the last 60-odd years. It's a phenomenon that's occurred all over the world. The impact of this extraordinary growth was revealed in a long-term research project involving 50 countries. It was called the International Geosphere-Biosphere Program.
It was the first recognition, I think, formally, that we need to understand more than the climate on its own. We need to understand the Earth as a system. We wanted to put all of what we learned together in some graphs, and we wanted to put 12 indicators of human activity and 12 indicators of the Earth system.
The 12 measures of human activity included primary energy use, transport and tourism.
We looked at the obvious ones. We looked at population, we looked at economy, GDP, we looked at large dams.
They charted the increasing use of water, fertiliser, paper and telecommunications. The graphs all started at 1750, just before the Industrial Revolution kicked off, and they all looked strikingly similar.
What absolutely shocked us when we looked at them was I expected to see a line pretty much going fairly evenly from 1750, maybe 1800, up to the present Industrial Revolution. What I saw was a very flat line from 1750, 1800, 1850, 1900. Then from about 1950, they all skyrocketed.
Although this post-war boom period was known to historians, what wasn't known was the corresponding shift in Earth system function.
We had the famous greenhouse gases. And again, they were creeping up from the Industrial Revolution for sure. CO2 is the one that everyone knows, but we also had methane, which is very important. And we had nitrous oxide, which people don't think about. It's very long-lived, associated with nitrogen fertilizers, with agriculture. The nitrogen cycle is hugely important. I would argue almost as important as the carbon cycle. All of them were creeping up from 1750, but again, you see a break point around 1950, going up very sharply. We looked at global surface temperature, again, very wiggly, but then from about 1960 or 1970, you see a sharp increase. We looked at the marine fish capture, and again, we see a sweeping up after 1950, but interestingly, we see a strong plateau from about 1995 or so to 2010. And you can say, oh, we've gotten smart, and we've gotten sustainable. The answer is no. The answer is we've just fished out the planet. We've fished out most of the large fishes and now going down. So these are extremely big changes in magnitude. And the systems around us that are used to geologically normal rates of change, Barrier Reef, southwest Tasmania, the boreal forests in Canada and Russia, can't cope with the rates of change that are occurring now. That's why we're seeing extensive bleaching, wildfires, insects in the north, and so on.
So what's the cause of this sudden and dramatic shift? It would be easy to look at the graphs and single out a rapidly rising population, but this would be a mistake.
What we found was the single biggest factor was actually consumption. And we found that 18% of the population was driving 74% of the global consumption. So even though stuff was being increasingly made in China and India, it was being consumed in the OECD countries.
It was named the Great Acceleration, a change so profound it's shifted the Earth system function outside Holocene boundaries. It's this that's led Earth system scientists to suggest we've entered a new geological epoch called the Anthropocene, in which humans are a force to rival nature.
What the Earth scientists are proposing is absolutely extraordinary. It's the most astonishing event, certainly in human history, almost a parallel with the arrival of life on Earth, because here we have a conscious force, an intelligent force that could send the Earth off in that direction or in that direction. This is completely unprecedented.
The word Anthropocene has caught on, appearing in popular articles and even science journals, but it's not a formal geological definition and doesn't appear in the official geological timescale.
Formally declaring a new epoch means more than just recognising that the world has changed. Those changes, no matter how extreme, must be recorded in the surface of the Earth itself, right across the globe.
Geologists, and particularly stratigraphers, are bureaucratic and formal and pernickety for good reason, because one of the jobs they have to do is to look after the geological timescale. And the timescale is meant to be a stable common language, not just between different geologists in different parts of the world, but also between generations. So any change that is made slowly and carefully and grudgingly, and only if there's overwhelming evidence.
So for the last 7 years, a working group of the International Commission on Stratigraphy have been assessing geological evidence for the Anthropocene's existence.
How do you reckon we would recognise Anthropocene in our succession?
Well, it's small, isn't it? So,
We're a group of individuals, 34 in total. We're experts in a whole variety of fields. What we're trying to do is go through evidence from the geological records. That could be from lake clays or from oceans, but also even things like living organisms such as corals and trees, or even caves.
I certainly didn't have an idea as to whether the concept would hold up geologically and firm up, or whether it would simply dissolve in a kind of haze of uncertainty. After some study, this mid-20th century really began to stand out, as the time of both the greatest change and also the greatest number of signals being impressed into strata now forming.
So we could include things like novel materials, things like aluminium, we've got concrete, plastics as well. There's geochemical signals, things like lead as well from the exhausts of cars.
The tops of sediment cores are also full of fly ash from the burning of fossil fuels.
They don't degrade with time, so you'll find that these particles, small spherical carbon-based particles, they suddenly increase very dramatically in the 1950s. Then there's things like temperature changes as well. They have an expression in the geological record which can be found.
Fossil assemblages are also changing, a traditional marker for defining new units of geological time.
The biological signal is very complex. The species that we keep to eat, the cows, the pig, the sheep, the goats, the chickens, the domestic animals, they outweigh, let's say, the total weight of wild animals on land because of the way we've bred them in a geologically very rapid time into a different shape. They will actually form differently shaped fossils. And that is the key element for stratigraphers, for paleontologists.
With a volume of evidence behind them, the Anthropocene Working Group came to their conclusion early this year.
We can now say the Holocene world has gone. We are in the beginnings of a transition to something else.
We're also in a broad agreement to say that we feel that this happened around about the mid-20th century.
The idea that a new geological epoch began just over 60 years ago has ruffled feathers in the geological community. Jim Gayling understands why.
Well, the Ediacaran period in this place is made up of 4 kilometres of rock formations. So if you were to put your finger on just one layer within the Ediacaran, that fingernail represents the total thickness of the Anthropocene. A geological effect is something that could be recorded for tens of millions of years, not just hundreds or thousands of years. I don't believe that we will one day point to a layer and say, here is the record of the Anthropocene. It's conceptual. Could happen that the Anthropocene becomes a physical geological event, but we won't be here to know about it, nor will our descendants be here. That's the problem from my point of view.
There is a difference in that we're living through it, for sure, but we're examining it in classically chronostratigraphic terms. So the important thing is that the Earth system is changing, and that is reflected in rock strata. It happens to be that humans are driving much of this change. But if it was not humans driving the change, the kind of change would be as profound and as important and as deserving of consideration for inclusion on the geological timescale.
So, Chris, I'm interested in this Staten Island core. Is this near to the Fresh Kills landfill site?
Yes, this is located.
It's far from a done deal. Before they can formally submit a proposal to declare the Anthropocene, the group needs to get their hands dirty.
It's a mixture of local roots that are actually...
The work so far has been a review of existing publications. The next phase of work is where we need to go out and actually find the evidence of this in specific sections. And we need to record the changes as they happen and show that there's a consistency in the change of those.
But the short timescale requires extremely high-resolution samples.
If you're accurate to within a few tens or hundreds of thousands of years, that's usually considered to be fairly accurate in geological terms. But for us, so ideally we're looking at things which have got annual lamination. So things like cave deposits, lake clays, even coral reefs.
Corals are a particularly good candidate for reference strata because they reliably lay down annual growth bands, just like trees. The Australian Institute of Marine Science in Townsville boasts the largest collection of coral cores in the world. It contains hundreds of cores from coral reefs all over Australia.
We mostly work with a species called Parietes, which is a really tough coral. We sort of call them tough old buggers because they'll grow in very clean waters, but they'll also grow in turbid inshore waters.
The growth bands are hard to see with the naked eye, but once X-rayed are easy to spot.
Right, so this is an X-ray of a slice from a massive coral, and what we can see is these density bands, what we call them.
Yeah, they're very clear all of a sudden.
They are, and we now know that those are annual bands, so we can date each of those years. So you've got these fantastic historical archives, sort of, I call them reef history books. The longest core that we have at Ames probably started growing about the time of the Black Death in Europe. More commonly, the big corals are maybe 200 years old, but that means for us we can get back prior to pre-industrial times in these coral records.
Under an ultraviolet lamp, some bands glow brightly. They reveal the increasing flood years during the Anthropocene.
With the luminescent bands, what they tell us is that the very big flood events seem to be coming more frequently and more intense than they used to be several centuries ago. Reconstructions of seawater temperatures from the strontium-calcium ratio in the coral skeletons also show this recent acceleration in warming.
The reason scientists discovered coral laid down annual bands was due to a series of radioactive events that occurred just over 60 years ago that left behind a chemical signature. Coincidentally, it's those same events that may mark the start of the Anthropocene.
The bomb is now at 8,500 feet, at 6,500 feet, at 4,500 feet, at 2,500 feet. Approaching 1,500 feet.
The best candidate for the golden spike probably stems from the nuclear test explosions, the atmospheric test explosions.
The advantage of nuclear fallout, and particularly things like plutonium, is that the first appearance of these in sediments in particular is pretty rapid. It's about 1952 is when you start to see a globally distributed signal. And accumulates can be found in the Antarctic, in the North Pole, and across the entire planet.
It will take several years to amass the evidence needed to submit a formal proposal. But in the meantime, there's urgent need for recognition of the Anthropocene outside the geological community.
I don't think very many people at all can understand really what's going on. First of all, those sort of curves that sweep up can't go on forever. It's just physically impossible. They won't. If we keep going on our present trajectory, we will drive, a single species will drive the 6th great extinction event in Earth history. We need fresh water, we need food, we need to draw these from ecosystems. But then there's services that stand behind that are important. A really classic one is pollination. Okay, that's really important for food systems, and yet species of bees are contracting in range, some are going extinct. In Southeast China, for example, you see pictures of Chinese people crawling trees with a big stick to pollinate blooms in the trees artificially because the bees have gone. The Indian monsoon, okay? That's a regular pattern of rainfall that allows 1 billion people to grow food. If we change atmosphere and oceanic circulation and the atmosphere by putting aerosols, pollution up there enough, we can flip that off like a switch. Probably the people who are most ignorant of this are economists. One group that does get it is actually the defense forces and the security people. They all understand that when you fundamentally change people's ability to grow food, provision themselves with fresh water and so on, you're going to have security problems. Syria has just gone through, in the last decade, the worst drought in its recorded history. Before things blew up, people had to start moving because people could not grow enough food to support themselves. And of course, when there are other tensions, for political reasons and so on, this is just a threat multiplier, as the security people talk about.
Just to prevent temperatures rising more than 2 degrees, a target most countries have signed up to, requires a drastic change of tack.
We have to leave nearly 90% of existing coal reserves in the ground. We have to leave half of gas reserves in the ground, about 35% of oil reserves in the ground. There's no Galilee Basin, no new gas, no new oil. And that's to have a 50-50 chance.
It is really the lukewarm frog effect. We don't feel the water beginning to boil around us. And that's why there's so much attention being brought to the concept of the Anthropocene. I've heard perfectly rational people say, well, it won't matter when I'm dead. Why are we here if things don't matter when we're dead? Of course they do. We are part of a community, and that community has a right to continued existence and continued existence in the presence of other organisms on the planet. And it's possible. We've got all of the expertise today to actually solve these problems. We just don't always have the will.
You know, I think it will take decades for people to understand what the Anthropocene means for humankind. I mean, it's a profound ethical, philosophical, theological rethinking that humankind has to do.
The Anthropocene is exceptionally powerful. It is a single word that encapsulates the problem we have and the challenge we have ahead of us.